Right. If you just do it, it turns out okay, even if things doesn't look like it at the beginning. Hey everyone, welcome back to Talking with Caffeine, the only podcast where we talk about whatever the hell we want to talk about and drink caffeine or eat caffeine or whatever. Anyways, special guest today. Introduce yourself.
Hi, I'm King Crocoduck. I'm a YouTuber, and yeah, some people listen to me for some reason.
Named yourself after a little Kirk Cameron picture.
Yeah, that's right. Kirk Cameron once argued on live television that if evolution were true, then we should be able to see a kind of offspring, a kind of hybrid of ducks and crocodiles called the crocoduck. That's where uh, my name comes from. It's just poking fun at that nonsense.
Oh, so I'm sure you've heard of this Kent Hovind guy.
I've done more than just hear of him. I debated him 3 times.
Yeah, I saw that debate.
Not the funnest thing I ever partook in, but people found it entertaining and educational, so I suppose that counts for something.
Yeah, speaking of Hovind, that's how I first saw your videos. Was your series on his kid?
Yes, the Eviscerating Eric Hovind series. That was my first major project on my YouTube channel many years ago.
Oh yeah, and then I watched your Ken Ham debate breakdown.
Yes, my longest ever video, I think. 2 hours or something.
Oh, but speaking of his daddy, he has this idea that evolution is like 6 different meanings.
Sorry?
What?
Could you repeat?
So, speaking of Hovind, his daddy thinks that evolution has 6 different meanings.
Yeah, that's something they like to push. It's a way for them to pigeonhole all of the disciplines that they don't like, the ones that contradict directly their biblical teachings, and give it all one name, so it looks like they're attacking only one scientific theory, when in fact they're attacking a zillion of them at the same time. It's not just this one aspect of science they disagree with, it's the entire scientific program. And these 6 quote-unquote definitions of evolution are a mechanism for concealing that.
Yeah, well, 2 weeks ago, my guest and I talked about the Big Bang Theory and what really happens. And today I figured we talk about the other one, next one in the list. But I just, talking about it, thinking about it, I discovered, don't you need the stellar stars to form before you even do chemical evolution, according to him? Again. Welcome back again.
Hello, can you hear me?
Yes.
Okay, cool. Excellent. Could you repeat it? Yeah, sorry about that. Could you repeat the question? There's a little bit of a network instability here.
Yeah, according to this list, I was thinking about it last week. Number 2 is chemical evolution. Blah 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 blah. But don't you need the number 3 one, stellar one, before you get to chemicals? Don't you need to start to even get to chemicals?
That's a good question. The answer is actually no. That's because nucleosynthesis, the process of creating more complex chemicals, actually began during the Big Bang, during what was called Big Bang nucleosynthesis.
Okay.
And what basically happened was the temperatures were so extreme. It was cool enough for stable nuclei to exist. It reached what was called the threshold energy. Once you reach a certain energy, it's impossible for certain things to form. So at a certain energy, it's impossible for chemical bonds to form. And then if you go up even higher at a certain energy, it's impossible for protons and neutrons to come together, and for electrons to be joined in as well. And as you increase the temperature, as you increase the energy, it becomes less and less possible for complex structures to form. You need it to be cooler. You need the universe to cool down much more than what it was at the beginning, in order to reach these more stable, more complex structures. And once it did that, within the first few seconds of the Big Bang, you had the generation of stable atomic nuclei, and then later on, it was possible for the temperature was high enough to allow certain nuclear reactions to take place and allow the formation of even more complex elements, mostly helium, but a little bit of beryllium, a bit of lithium, some amount of the other trace elements.
Okay. So the basics elements were formed during the Big Bang and before stars were formed.
That's right. All that you need in order to have the most basic element, hydrogen, is a proton. If you have a proton, you have hydrogen. If you have hydrogen, you have the building blocks for everything else.
All right. So then, how did the first stars get formed then?
Well, gravitational attraction started to pull the hydrogens together, and you eventually had these massive clouds of gas that started collapsing in on themselves. And as they did so, the temperature became sufficient to allow for the Coulomb barrier to be overcome. And what that basically means is protons are positively charged, right? They have a positive electrical charge, and like charges don't like each other. They tend to repel each other. So you have these two competing forces. You have gravity that's pulling the hydrogens in close to each other, but then you have this electrostatic force that's pushing them away from each other because of their positive electrical charges. But eventually, the temperature allows this barrier that exists as a consequence of these electrostatic forces to be overcome. That's called the Coulomb barrier. And at these incredibly high energies, facilitated both by gravity and by the latent temperature of the early universe, what happened was the protons were able to cross over these Coulomb barriers and engage in nuclear fusion. And what this effectively amounts to is you have two hydrogen atoms, so two protons, they both have the same mass, and they then stick to each other, for lack of a better word. They fuse together to form a helium atom, but the resulting helium atom has less mass than the two separate hydrogen atoms. Well, where did that extra mass go? And the answer is it turned into energy in accordance with Einstein's famous formula. And that kind of reaction is what sustains stars. It's what allows them to exist.
D equals MC squared formula?
Yeah, as well as a certain modification of it.
Okay. So, and where about the neutrons? Where they come from? Are they there too, or are they?
So neutrons. So both protons and neutrons actually exist as a consequence of even more fundamental particles called quarks. And there are 6 different flavors of quark, 6 different types of quarks. They're called up, down, strange, charm, top, and bottom. And in order, you can form all kinds of nucleons using these 6 different things if you combine them in the right way, in accordance with certain rules that quantum field theorists discovered back in the 40s and 50s. And to create a proton, so to create a hydrogen atom, you need an up quark, a down quark, and an up quark. You combine those together, and you get yourself a proton. But for a neutron, you need a down, an up, and a down. So for proton, 2 ups and a down. For a neutron, 2 downs and an up. And neutrons were developed during the Big Bang nucleosynthesis. But there are other processes that can generate neutrons.
Yeah, I recently learned that the elemental number of an atom is the number of protons it has, but then the weight of it is the proton and neutron together.
Sorry, could you repeat what you said?
Sorry, a few years ago I recently learned, not recently, but a few years ago, that the elemental number of an atom, is the number of protons it has, but then it also has a weight thing, which is the protons and neutrons together.
Right. The atomic mass is going to be your protons plus your neutrons. The neutrons do contribute substantially to the mass, but the atomic number itself is only a contribution of the protons.
Yeah, and it probably has the same number of protons and electrons, but the neutrons could be any number of. Sometimes the same number, sometimes they're not. Right.
So you can actually have whatever combination. Well, I shouldn't say that. You can have protons in an atom having the same number as neutrons and the same number of electrons. That's possible, but it's also possible for none of those things to be equal.
Oh.
In the case where you don't have the same number of electrons as you do
Hello? Hello? Did I go deaf or something?
Hello?
Yeah.
So for example, with hydrogen, the most common type of isotope is just the proton by itself. But then there's another isotope called the deuteron, which is the proton and the neutron together. And then there's another isotope called tritium, and that's a proton with 2 neutrons. And those are all hydrogen atoms because they all have 1 proton. But they can differ in terms of their mass because they'll have different amounts of neutrons, and that's what it means for them to be different isotopes.
Okay, so one would be hydrogen 1, hydrogen 2, and hydrogen 3 then.
Yeah.
All right. So I heard that when it comes to few nuclear synthesis or whatever, stars can only go up to like iron by themselves.
Right. So that has to do with the efficiency of the nuclear reaction. The existence of a star is a precarious one where it's carrying out a kind of balancing act, and it has to balance 2 opposing sets of forces. The nuclear reactions that are generated in the core, so the hydrogens fusing into helium and later the heliums into carbon and blah, 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 that all happens. When that happens, you have a net force outward from the core. The energy, it pushes isotropically out of the core. But you also have another force, and that's gravity, and gravity is pushing in the opposite direction. And these 2 forces are opposed to each other. So the star, the various properties of the star, including its size and its temperature and all of these various things, are basically governed by where along this point of equilibrium the star is. So you can have a star that has a tremendous amount of mass, and it needs to sustain a tremendous amount of fusion in order to be able to keep that mass from falling in on itself. You have to have these forces in balance. Whereas a smaller star, it'll have less mass, so it'll engage in less fusion in order to sustain its size. And when you make your way up the periodic table of elements, once it runs out of hydrogen and starts burning helium into carbon and starts, moving up this periodic table, eventually it gets to iron. And that nuclear reaction is unsustainable in terms of the outward force. So at this point, gravity begins to take over, and it crushes the star. And depending on the size of the star, a number of different things can happen, but it concludes basically with the death of the star.
And that energy maybe gets higher elements.
So it depends. If the result is a supernova, so basically the star collapses in on itself, and the result is a massive explosion. What will happen is the temperatures associated with the supernova are going to be so tremendous that a special process called neutron capture reaction is going to take place. This can only happen at extreme temperatures, the kind of temperatures you get from a supernova. And what basically happens is at these temperatures, different atoms with both protons and neutrons are going to start exchanging their neutrons with each other. And these neutrons are going to decay into protons. So the neutron, so the down, up, down turns into an up, down, up. And of course, when you increase the number of protons, so if you have an element with, say, 10 protons, and then it accepts 3 neutrons, and then those 3 neutrons turn into protons, now you have 13 protons in that atom, and now it's a different element. And that's basically the kind of process that takes place in a supernova. And that's how you get your elements that are higher than iron.
Okay.
Does that make sense?
Yeah. So like iron's 26, right? If I remember correctly.
I don't remember off the top of my head. You'll have to consult with the periodic table.
Yeah, I think, but yeah, but and forming nuclear synthesis is what's called, right? That's different than forming compounds or molecules, right?
Sorry, say again?
The two atoms, like what's called nuclear synthesis.
Stellar nucleosynthesis.
Yeah, that's different than molecules, making compound molecules, right? Those.
Right. Yeah, you can form molecules without Big Bang or without stellar nucleosynthesis. If you have hydrogens, you can have the hydrogens bond together and get H2, and you don't need stellar nucleosynthesis for that. But if you want to make things more complex than that, then yeah, you will need stellar nucleosynthesis. So if you want to get H2O, for example, then yeah, you're gonna need that oxygen. And that can only be created.
And we lost him again. We see muted again.
You can't hear me.
I can hear you now.
Okay. What was the last thing you heard?
If you want anything more complex like water.
Yeah, then you're going to need that oxygen, right? Water is H2O, and that O is not going to come from the Big Bang, at least not in the quantities that you needed. That's only going to come from stellar nucleosynthesis. So that's how you produce your more complex stuff.
Are you on a phone or something, or your mic internet going in and out?
No, I'm on the phone, but that's usually not a problem.
Yeah. Usually is it? Yeah. This thing is still in beta, so I guess phones are still an issue here and there sometimes. But yeah, but we can work on it. I had the same problem with Tony Reed when he had his phone on. So
sure. Well, just let me know if you can't hear me, and we'll try to see with it what works out.
All right. So go for the big man. All right. So what happens? Okay, all these things are formed and explode. So what happens after? So how long do these? So the first stars probably died about 10 billion years ago. The first stars were formed and died are died by now, most likely.
Yeah, that sounds plausible.
So what happens after all of these elements are scattered to the wind, or after the stars exploded?
Well, the same process repeats. They'll start attracting to each other gravitationally, and they're going to form another star eventually. Once nuclear reactions, well, once it becomes hot enough for nuclear reactions to take place. And sometimes the heavier elements are going to, what should we call it? Well, think about it in terms of density. Get a bottle of water, put an ice cube inside, and then put a rock inside. One of these is going to float, one of these is going to sink, and that has to do with the relative density in relation to water. So something similar is going to happen during this process called accretion. You're going to have this differentiation of materials based on their relative density to one another. So in the middle, in the middle of this whole process, you have the star that's forming, and it's constantly generating new gases, and that's sort of the core of the solar system that's being formed. And then a little bit outside of that, you have the densest material, the stuff that's closest to the bottom. So things made out of iron and nickel and silicates, these are your terrestrial planets. And then you move out further and there's your less dense material, your gases, and those coalesce to form your gas giants.
The gases that weren't absorbed by the formation of the star.
Right. Or were outright ejected during this process. The sun is constantly spitting out gases, and during its early history, it might be possible that it did this to a greater extent than what it's doing now. But these gases and this stuff is all attracted gravitationally to the sun. The sun is a massive thing. And then if you go even further, you get even less dense stuff. So individual chunks of ice just floating out there.
Like the Kuiper belt and the Oort cloud.
Yeah.
All right. So,
although I should stress that the Oort cloud might not necessarily have been the result of the production of the sun. That's a separate thing. Excuse me.
Okay. So accretion is different from like when planets form and balls like asteroids form. That's different from when the gravity formed the star, right?
Sorry, could you repeat that?
Sorry. Accretion when a planet comes together or big bodies of rocks, that's a different set. That's a different process than when the gravity makes the star form.
Well, fundamentally, gravity is involved in both of these processes. It's just that when the formation of a star, it's primarily acting on gases, and with planets, it's acting. Well, for the terrestrial planets, it's principally acting on silicates and iron and nickel and things like that. But again, as you go outward to the gas giants, again, you have accretion of gases there as well. So anytime you have things coming together through gravity to form large spherical bodies, and these bodies aren't necessarily going to be sustaining themselves through nuclear fusion, you have accretion. That we call that accretion.
Okay. So do we know why the gas body planets further out didn't form like stars themselves?
Yeah, because of the relative densities of the materials that are getting spit out. So you have to understand, solar systems are generally formed from the remnants of dead stars. So the stuff that's actually going to be producing the nuclear fusion, that material is going to form the core of the solar system, the most internal part. And any gases that are far away enough from that to not be part of that process, those are eventually going to accrete into gas giants rather than end up being swallowed by the sun. Because, again, you have this process of differentiation. where the more dense materials, these rocks, these silicates, are moving closer to the core, and the gases are diffusing further away.
All right. So, what about two-star systems?
I don't know all that much about binary star systems. That sounds like a question for Landon.
Okay. So off topic of this, what got you interested in all this?
Well, I'm a physicist. This is all interesting to me. If it concerns physics, then I'd like to know about it.
Okay. And what got you interested in physics?
Oh man, that's a story. Probably a story for another time, to be honest. But I will say that when I first got into high school, my intentions were to become a lawyer and then a judge and eventually Supreme Justice or Justice of the Supreme Court.
Well, how times have changed.
Yeah, so don't rule anything out, I would say, to any young people who are watching. Keep an open mind. Anything can happen.
I see now. The first physicist on the Supreme Court.
Well, I wouldn't have been a physicist if I had chosen this other route. Yeah.
All right. So accretion. Right. Any other processes to happen?
There's all kinds of interesting things happening in the universe. You have the formation of neutron stars. That's an interesting topic on all of its own. Of course, you have the formation of black holes. Everybody likes those. You get
black holes. Are they all former stars?
As far as we know, in principle, they don't have to be. In principle,
Okay.
you could take something like the Earth and crunch it down to a certain size. Once it meets a certain threshold of size called the Schwarzschild radius, at that point it does become a black hole. But stars are the only mechanism that we know of that do generate black holes.
Speaking of black holes on the Earth, did you ever hear that strange theory that the Earth is in the middle of a black hole?
No, but I'll be honest, it kind of sounds like crap.
Yeah, I forget where I read it from, but it was the theory that I guess it was like some kind of creationist theory. That's why the Earth is 6,000 years old, everything else is longer because the Earth is a time warp or something like that.
Yeah, that's bullshit. If the Earth had been in the presence of the kind of conditions that are involved with the black hole, there would be no more Earth. It would have been completely spaghettified.
Did you ever see that movie Interstellar, I think it's called?
I did not, so don't spoil it for me.
Okay, never mind then. I was going to ask you about something that happened in that movie, but you haven't seen it yet. So, all right, never mind then.
So, what is it about Kent's, Kent's point of view that we're tackling here exactly?
Well, basically, he said at the beginning where he thinks that all of science, is one big thing with separate subjects.
Well, I guess that's the goal. Eventually unify all knowledge into a single coherent set of theories that are all connected to each other. But no, science hasn't reached that state yet, and certainly you can't slap the label of evolution on it. It's much more complex than. Like I said at the beginning, this equivocation between all these different fields of science and evolution is just the creationist way of giving one name to the entire vast body of science that they don't like.
So instead of tackling each subject individually, they lump together and says this is all wrong. So.
Right, but for the purposes of PR, it doesn't look good if you say everything in science is wrong. if you just say, oh, I disagree with this one specific theory, and then when you unpack what they mean by this theory, it turns out it's all of science. This is better for PR than just admitting outright that you're against pretty much all of, almost all of what science has discovered in the past 150 years.
Speaking of anti-science people, have you ever had to deal with flat earthers?
Not directly. Why?
I was just wondering because thinking about people that deny science and stuff.
Yeah, flat earthers can be frustrating, but I don't think I've ever. I mean, I think maybe I did encounter one time on Steve McRae's show many years ago, but all I remember of that encounter is face palming, which is maybe why. That's all I remember of it.
You got a concussion and you walked it out.
Yeah, there you go.
All right. So how the atom and quarks are part of neutrons and protons. What about electrons? How do they get around?
So electrons belong to a different, we might say, class of particle called a lepton. They have certain unique properties that things like protons, things like quarks and photons don't have. But they were a property of the very early conditions of the universe. They're a fundamental particle, so they've been around forever. And as far as we know, there's nothing that makes up an electron. An electron is just its own individual point, for lack of a better term. And there are a variety of mechanisms by which electrons can be captured by different elements, and the affinity of an element to capture a particular electron is referred to as its electronegativity, how good it is at catching and sustaining electrons. And of course, there are a variety of mechanisms that take electrons away from atoms. So, that's does that answer your question?
Yeah, pretty much. But anything more complicated probably go over my head.
Well, don't be afraid of trying.
Yeah. Okay. Fusion is different than fission, right?
Yes, they're actually kind of opposite processes. With fusion, you take two masses, you stick them together, and you end up releasing energy that sort of splits the difference. And so I was describing earlier, you can have two hydrogen atoms that both have a certain mass x, and then you can have, when you put them together, the total mass should be 2x, but the helium atom with just two protons, ignoring any neutrons, is less than 2x. That extra mass gets released in the form of energy. That process is nuclear fusion. Whereas nuclear fission, what you have is an unstable isotope. So an atom whose nucleus is just too big, the Coulomb forces are too unstable in that atom. The electrostatic forces that are involved. Things are breaking themselves apart, and eventually, you can think of fission as kind of a mechanism by which unstable atoms turn into more stable decay products. And of course, they release quite a bit of energy as well.
So it's in terms of decay products. Is that how that the process that once we date the dating of the rocks and stuff, right? Like radiometric dating, stuff like that, and carbon dating?
Yeah, radiometric dating does follow the principles of radioactive decay. Yeah. Different elements will decay at different rates, or I should say they have different probabilities of decaying, and when you aggregate those probabilities, that turns into different amounts of decay per time. So we would say different activities of these elements. And yeah, you can use these different types of elements to, using different equations. Well, the same basic equation. It's an exponential decay function, but there's a different constant in each one depending on the type of element you're working with. And so you can take the same material, and you can use applicable dating methods, applicable applicable radioisotopes, and start dating those, and you'll see that they cross-confirm each other. So different dating methods will all say the same thing: the Earth is billions of years old, not thousands.
All right. I've always wondered this personal opinion. I guess it's not an opinion or not. I think, how many of the stars do you think out there right now still exist right now?
The ones that you can see with the naked eye, my estimate would be that most of them are still around. But if you look out with a telescope at stars outside of our own galaxy, I'd say most of them died a long time ago. But that's just my own back of the envelope kind of estimate. People who are better versed in astronomy than me are free to disagree. But the basic principle is, the closer the stars, the more likely it is that they're still alive, because it takes less time for their light to reach us. But the farther away they are, the more likely it is they died a long time ago, because by the time their light reached us, they're already zillions of years old.
Okay, I was wondering about that. Just a thing that I was wondering about, thinking about that, since stars are light years away, So, Right,
is it possible we might maybe get some Q&A from the chat?
Sure. Hey, chat, you have any questions? While we're waiting for that, how come, I know gravity is a thing, and organization. So how come the sun didn't, gravity in the sun didn't bring all this stuff back together, suck everything into the sun, but instead it starts revolving around the sun?
There's a limited amount of mass, so there's going to be a limited amount of gravity. When these things first started moving, they started moving along a certain trajectory, and they are, quote unquote, falling into the sun. That's basically how orbits work. But it's not falling in. It's not falling directly into the sun. It's undergoing elliptical motion. And whenever you have elliptical motion, or any motion that changes direction at every point along the trajectory, you are you are always accelerating the body. And as long as you're accelerating the body, it's under the influence of gravity. So it is, in a sense, falling into the sun. It's just more falling around the sun. That's sort of the explanation.
Okay.
If it was falling into the sun, it would go slowly at first and then pick up speed and faster until it crashes into it, right? It accelerates under the influence of gravity. And it is, these planets are accelerating under the influence of gravity. It's just that they're undergoing elliptical motion instead of crashing right into it.
Yeah, first question.
It's the reason why our satellites are in orbit around the Earth instead of falling back into the Earth. Why the moon doesn't fall into the Earth, right?
You see the question?
Yeah, Blue Horizons is asking, if the Big Bang is an explosion of a bunch of hot and dense state, where did that stuff come from? So, if the question is where the energy from the Big Bang came from, I'd say that based on the physics that we know of, the energy has always existed. That's just the first law of thermodynamics. But how it how it came to be that you have whatever state there was prior to the Big Bang, and then the Big Bang itself. Nobody knows. That's the simple answer. We don't have any physics that can help us out there. In order to understand the kind of system that the universe was in its first moments, we need a quantum theory of gravity, and we need to unite that theory of gravity with all of the other fundamental forces.
I think your phone died again.
Sorry, can you hear me?
Yes, I can hear you again.
Okay, yeah. So you need a quantum theory of gravity in order to be able to even touch that kind of topic. And there are quantum theories of gravity. The two main contenders are string theory and loop quantum gravity. And they have a zillion different possible explanations for how it could have happened. But at this point of time, there's just no way of telling.
A personal question now. You just have a bachelor's, or you have a master's, you have a doctorate?
I have a master's in physics, and right now I'm taking the next step in biomedical physics. I'm still a graduate student, but with a master's degree.
Oh, so you're going for your doctorate?
I can't confirm or deny anything just for doxing reasons.
Oh, okay.
It's just there's a limited number of programs in the country, and if I give too many, and there are different types of degrees awarded. So, for example, there's a PhD, there's a DMP, and there's a master's, and these all have specific institutions or specific sets of institutions assigned with them. So people know what exactly it is I'm doing, and they're able to, yeah.
I was make a joke. It said, if you ever debate Ken again, he said, "This is Dr. Crocoduck."
Sorry?
It was a joke, if you ever debate Dr. Dino Hovind again, you can say, "Hi, I'm Dr. Crocoduck."
Well, I can already say that. It just won't be true. Same as Kent Hovind. He says he's a doctor. It's also not true. It doesn't really matter what you call yourself, as the debate showed. I had only a bachelor's degree at the time that the debate took place, and I whooped his ass, even though he called himself doctor. So, take from that what you will.
Yeah, right. Another question.
How do you even know that quantum gravity would do anything? Bruh moment. The basic reasoning is this. As you go back further in time, the universe becomes hotter, and as the universe becomes hotter, you reach the threshold energies at which the different forces start to combine into one force. So we have four fundamental forces in the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. And if you go back in time to a certain point in the Big Bang, there are actually only three fundamental forces. You have the strong nuclear force, the gravitational force, and the electroweak force. And the electroweak force is the combination of electromagnetism and the weak nuclear force. And then if you go back even further, those three forces turn into two. You have a gravitational force, and you have the grand unified force. So the grand unified force will only contain electromagnetism, the strong nuclear force, and the weak nuclear force. So you have only these two forces operating in this regime, and we do have a decent idea of how things worked when these two forces were in play. So the idea is, if you go back even further, these two forces would turn into one force, and that would be the force associated with the theory of everything, the force that would be described by quantum gravity. And string theory and loop quantum gravity claim to be descriptions of this force. Maybe they are, maybe they're not, who knows. But yeah, it might be possible that this assumption isn't even warranted. It might be the case that if you go back in time further, these two forces are actually accompanied by a third one that only exists at a certain regime, or that third other force, well, we'll call it quintessence, if you like, exists to the exclusion of these other two. We have no idea. It could be this assumption is completely wrong, but based on patterns that have been observed in particle physics and in collider experiments, this is kind of the trajectory. This is the reasoning that was taken.
All right. So look at that. What subject in physics are you like? What you have a are you studying all physics? You have a specific branch that you're studying.
Yeah, biomedical physics.
By so what is that?
It's actually a pretty broad field.
Ah,
It ranges from using physics to describe biological systems, complex biological systems like the human brain, which my earlier research did. And it extends to the clinical field, mainly in radiotherapeutic physics. So that's where I'm currently working on trying to develop and understand better radiation therapy and trying to understand the radiobiology associated with that.
okay. I Anybody have any other questions or not? This might be a short podcast today.
Yeah, seems like a good place to wrap up.
I just I give it a few minutes, a few seconds. See anybody else wants to ask anything. All right, so all right, while we're waiting, are you not active on YouTube anymore, or do you like? Do
Yes,
you have anything?
yes, but I've taken a bit of a sabbatical. I've just been very busy these past few months.
All right, so, so you have nothing planned in the near future.
I've got a lot planned. It's just a question of execution. But don't worry,
Yeah,
the King Crocoduck is not dead.
yeah. I've had a lot more time to make videos lately since I'm not doing anything since I can't really go anywhere. Yeah. Has this thing affected you? Has this thing have affected you at all? This lockdown in your school studies?
Sure, it's affected everyone. Studies, teaching, research, but we'll just have to adapt and overcome.
That's true. All right. Well,
Hey, listen, this has been a great chat. I'm glad to have been part of it. So thank you for inviting me on here.
if you ever want to come back, just get my email address.
Cool.
All right.
All right.
Hey, everyone, never stop learning and enjoy the randomness. We'll see you all next time. Bye.